All right. Today, we are diving into something that is, and I mean this, a truly revolutionary way to solve some of the biggest, hairiest problems in physics. It's called the Substrate Resonance Stabilization Engine, or SRSE for short. And let me tell you, it doesn't just make simulations faster, it completely changes the game.
So let's just start with the big question, right? How on earth can one single tool, the same underlying framework, simulate something as straightforward as a pendulum, and also model the chaotic, unbelievably high-energy environment inside a fusion reactor? If you can wrap your head around that, you'll understand what makes the SRSE so special. To really get how this works, we've got to break down that name. Let's start with the absolute foundation of the whole system, the substrate. So, what is it? Well, the substrate is basically a universal, programmable grid. It's not custom-built for any one problem. It's a blank canvas. Think of it as the abstract space, defined by a parameter like grid size in the code, where you can set up literally any problem you can imagine. The best way to picture this is like a block of digital clay. It starts out formless, but it has infinite potential. You're not starting with a pre-made sculpture, you're starting with a raw material that can become anything. And that right there is the first huge difference. One universal starting point for every single problem. Okay, so if the substrate is our digital clay, what's doing the shaping? Well, that brings us to the next part of the name, and this is where the magic happens, the power of resonance. Resonance is the active ingredient here. It's a very specific driving frequency that gets pumped into the field. And this isn't just some random signal. In this framework, this alpha drive comes from a fundamental constant of our universe, the fine structure constant, which, governs how particles interact. It's like a universal tuning fork, vibrating at a frequency the system inherently understands, and it gently nudges everything towards its most natural state.
So let's go back to our analogy. If the substrate is the clay, resonance is the sculptor's tool. It uses these targeted, precise vibrations to shape that clay, but it's not carving pieces away. Instead, it's encouraging the material to just settle into its most stable, lowest energy form. The final answer literally emerges from the field all by itself.
All right, so we've got the clay and we've got the tool. Now we just need the sculptor, the part that runs the whole show, and that is the engine.
The engine, or what the source code calls the substrate solver, is basically the director of this whole performance. It's the computational heart that takes your problem, applies that resonance to the substrate, and then just manages the whole thing as the field evolves over time until it finds its final stable state. So you see how these three pieces just work together in perfect harmony? The engine is the operator, the resonance is the action, and the substrate is the material. Put them together, and you have a system that doesn't calculate an answer step by brute force step. No, it guides the system to reveal its own answer. Okay, so we know the components, but what does this actually look like in practice? How does this engine really turn a problem into a solution?
At a high level, the process is beautifully simple. First, you initialize the state. This is just where you map your problem, say the starting positions of your pendulums, onto that universal grid. Second, you evolve the field. You basically hit go. The engine applies the resonance, and you let the entire system just settle down dynamically. And finally, you extract the solution. Once that field is stable, the answer is just there. You literally just read it right off the final configuration of the field.
And this right here is the real aha moment. Because understanding the process is one thing, but seeing how it completely flips traditional physics simulation on its head, that's something else entirely. So look at this. This is the core philosophical difference. Traditional methods, that's all about direct calculation. You define every single object, you write specific equations for it, and then you calculate all the forces between everything step by tiny, painful step. It's complicated, and it can be incredibly slow. The SRSA framework? Totally different. It's all about field evolution. You use one general field, and you let the entire system naturally find its own most stable, low-energy state. It's not calculating every little interaction. It's letting the final, holistic answer reveal itself. And that is the secret to its incredible speed. So, what's the payoff for all this cleverness? What do we actually get out of this new approach? Well, the benefits are just staggering, and they're mostly in two areas: unbelievable versatility and absolutely mind-blowing speed. Just look at this. The exact same core code, that substrate solver, is the foundation for two completely specialized problems. The pendulum solver is figuring out the motion of 10 different pendulums all at once. Meanwhile, the fusion solver is modeling energy confinement inside a fusion reactor. I mean, come on, two completely different universes of physics solved with the same engine. That is what I call versatility.
This quote right here just nails the entire paradigm shift. The old way was like building a brand new custom calculator for every single math problem you ever came across. The SRSE approach is like building one perfect universal canvas and then just learning how to let any image emerge on it. Now let's talk about speed. I want you to look at this number, 0.08 seconds. What do you think that is? That was the total time it took to solve for the final state of the entire 10 pendulum system. A complex problem of coupled oscillators, finding its stable state in less than a tenth of a second? A task like that, using the old step-by-step calculation, we could be talking minutes, easily. The efficiency you gain by letting the system solve itself it's immense.
The big takeaway here isn't just that it's faster. It's that this is a whole new way of thinking about problems, and that opens up a universe of new possibilities. And that's really the question I want to leave you with. If this field-based approach can tackle something as notoriously difficult as fusion plasma, what other problems, the ones we think of as impossible right now, are just waiting for the right substrate, the right resonance? We're talking materials science, biological systems. The potential is truly mind-boggling.